Hello, and thanks for joining me on the floor today. Today we have something a bit out of the ordinary. Here I've got a Mole Richardson control panel from an arc lamp or discharge lamp power supply unit. Now this was thrown out at work a couple of days ago and I thought I'd pick it up. As I said, this is only the control panel. We also had the proper lamp unit and also the actual power supply unit that contained the transformer and rectifier, which was about the same footprint but about a meter tall. So I didn't rescue any of that from the scrapman, but this one I took home and I think we should take a look inside and take it to bits because there are some really exciting and useful things in there. But before I take out the large screwdrivers and take this thing to bits, I thought I'd just also quickly give you an overview of how an arc lamp has to be driven and how this thing fits into the whole picture. And we can also turn it on as well because it does do a few interesting things even without the power supply and the lamp attached to it. This is a picture of the lamp that this unit was originally used with. You can see that it's basically two big electrodes in a glass envelope and that is filled with a gas of some sort. And the way an arc lamp or discharge lamp works is you basically create a high current arc between the two electrodes. In this case you're talking about something in the area of 200 amps or so, and that arc is obviously very bright and this is how you get the light out. And you'll also notice that there is a third electrode sticking into the bulb, and the point of that is to just get the lamp started. So if you imagine you've got your 30 or 40 volts stuck across the two main electrodes, nothing much will happen because it's just a gas in there, so there's no reason for it to start an arc. So what you do to get the lamp started is you apply a high voltage arc between those two electrodes that are close to each other, and that ionizes the gas and gets the plasma started, and then your main arc will soon develop between the main electrodes. And really that's the entire purpose of this control panel, to strike the lamp and to control the current through the main electrodes. The first thing you would have done is obviously turn the control panel on, and you've got this very large switch here. I guess the next thing you would have probably done is to set the power of the lamp here with this switch. Again, it's a extremely large and loud switch, and actually does hurt your fingers a bit from the recoil of the spring. But anyway, we've got the unit turned on, we've got the lamp power set, but the lamp isn't lit yet because there is no arc in there yet. We've just got our 36 volts or whatever between the two main electrodes. And as I said before, in order to actually strike the lamp, we need to provide a high voltage pulse to that auxiliary electrode. And in order to simulate that, I've got those two wires here coming out of the back of the unit. One of them is from the connection for the positive electrode for the lamp, and the other one is for that high voltage auxiliary electrode from the lamp. And you can see that they terminate in that nice yellow and green wire because it's obviously completely safe to touch at the moment. So all we need to do to get the lamp going is hit this nice red strike button here, which I shall do now. And as you can see, this gives us a very nice and angry sounding arc between those two electrodes, which ultimately would get the lamp going. I'm not quite sure if you could see it that well, so let's just take a closer look at the arc itself. There is one thing which I'm not quite sure how the unit would have been used, and that's to do with this flash button here. At the moment there is a relatively high value resistor in series with the lamp, which probably means that it's not outputting its full power. So although we've got it set to 7.5 kilowatts here, it's probably outputting, I don't know, maybe 1 kilowatt or half a kilowatt or something like that. And I think you would use that to actually aim the lamp at whatever you want to illuminate, and then you hit this flash button here and you could hear a contactor inside turning on for a few seconds, and during that time that high value resistor would be shorted and the full power, or the power that's set on the switch, would be applied to the lamp. And lastly, on this side here we have external sockets. This one here is actually still the original one, which looks well, quite old. This one here was fitted at some point with a rather modern socket. I think it even has a RS part number on it. Big screw in the case, £1 coin, fits like a glove. I wonder if that was intentional. So down in here we have a spark gap, which is part of the high voltage generator system. So again, we turn on the control panel and hit the strike button. And you can see there is this lovely blue and red orangey glow inside the spark gap when it's generating the high voltage, and it's just an absolute thing of beauty. So let's start our exploration tour on the back of the unit. Over here we have all the terminals that came from the transformer and rectifier unit. We have a 24 volt input, which, as I said earlier, is to power the control panel itself and also the high voltage generator. And you've got this 36 volt terminal, which is for the actual lamp current. The lamp itself connects over here on this side. Those two terminals go to the main electrodes of the lamp, and this connector here is for the auxiliary electrode to strike the lamp. So this is where the high voltage comes out eventually. The 36 volts come in here and they go straight up here through here, and this here is the shunt resistor. Those two wires here go straight to the front panel ammeter. So it goes through the shunt resistor and then it goes straight to the main switch on the front panel here. Once it's gone through the main switch, it comes back up here on this line, and these two spirally looking guys are actually resistors. And you can see they're actually just a long spiral of metal on sort of ceramic bricks in the middle. So the current comes in here, it goes through this first resistor, and then it splits off, going down here, through this other bit of resistor down here, and through a bit more resistor down there. These two wires here go to the selector switch on the front to select the power. So if you're on your 7.5 kilowatt settings, it taps off the current here. In the 5 kilowatt setting, it taps it off here. And in the 2.5 kilowatt setting, it taps it off here. So all the switch on the front does, it just picks a bigger resistor to be in the path of the current. This big resistor here, that can get shorted with a contactor that's in the front, so it shorts those two terminals out. And that is the one that switches between the sort of normal mode and the flash mode. So if you just turn on the lamp, this resistor is in series with the lamp current, and then when you hit the flash button, this resistor gets shorted out and the lamp current goes straight through here to your selector switch. And just to give you an idea of the resistor values, this long resistor here is around 500 milliohms. This little section in here is around 25 milliohms, and that one here is around 100 milliohms. So I just took off the front panel, and as you can see, we already have a much better view on everything. Unfortunately, I also had to take out the rotary switch and the main switch because they're on fairly short leads and I couldn't have them in the front panel while taking the front panel off. So what I think I should do is disconnect those switches completely so we can have a close look at them separately, and once they're out of the way we should have a really good view on all the little bits and pieces in the instrument. With those two switches out of the way now, we have a much better view on the inside of the instrument. First, let's look at the switches themselves though. This here is the main switch, and as you would expect from the outside, it is very chunky on the inside, and it is extremely, well, it takes a lot of force, as I said, to actually use it, and when it's not mounted to the front panel it's even more difficult to switch. If you look very closely on the top here, you might be able to just about make out the rating. It says Made in England down here, and up here it says 60 amp 250 volts, and again, oops, made in England down here. So this switch is rated for 60 amps. As we've worked out, the lamp itself needs about 100-200 amps when it's at full power, so presumably that means that you should only switch the unit off when it isn't at high power, because otherwise that switch probably couldn't break the 100 or 200 amps. Similarly, we have the rotary switch here. Again, very chunky. I mean, just look at that spring, and there's two of those on each side. So, you know, just those springs themselves give it quite a bit of heft. On the back here we have, again, England. I mean, back then people were still proud of stuff being made in England. And again, it has maximum current 60 amps, which again probably means that you shouldn't change the power setting while the lamp is at high power, but maybe it's fine when it's at low power. And I'm not sure how apparent it is from the video, but the insides are extremely grubby. So these are my fingers just after taking out the switches. And now that we have a much better view of the insides, we can have a look at the high voltage generator, which is all of this here. This unit here generates not quite the final high voltage, and that's the loud, angry sounding electromechanical bit, which we have to look at later. You've got your output voltage coming through this wire here, going through here into the capacitor. And then we have a circuit that is found quite often in things like Tesla coils, for example. This capacitor charges up, and then you've got a spark gap between one end of the capacitor through a transformer and the other end of the capacitor. And the way that works is that as the capacitor charges up, at some point the spark gap will break down, which then means you get a very large current pulse through the primary of this transformer, and that current pulse then induces a very high voltage in the secondary of the transformer, which then goes straight out to the connector for the auxiliary electrode. The other end of the high voltage is clamped to the positive electrode of the lamp, and that goes through this resistor here, and that is switched onto the 36 volt line through this solenoid relay on the back there. We also have this chunky unit in the front here, and that is what bridges the large resistor on the back when we switch to flash mode. Over on this side we have what I believe is some sort of timer circuit. There are 4 capacitors and 4 potentiometers here. At least 3 of those capacitors and resistors are used to set the on time when you hit the flash button, so they set for how long the lamp is at high power for each different power setting. All of these timing capacitors go into those 2 relays down here. One of the relays controls this contactor here, and the other relay controls that contactor on the back that's responsible for turning on the high voltage generator. Well, I spent all of last evening taking the control panel apart, and this is the result. As you can see, everything is a bit more compact now, and I would suggest we have a look at all the different bits and pieces that were inside the control panel. Let's start off with the switches. We've already seen this guy, as I said before, a very nice and large switch, which will no doubt find use in another instrument at some point. Then there is this switch, which we've already seen as well, and again, I hope that I can find some use for that at some point in the future. And here we have a handful of those push buttons from the front panel, and these are quite interesting. They're actually really simple. All you have is these contacts on the back, which are just these bent bits of metal, and you've got this washer on a spring here, which when it's down makes contact between those 2 contacts, and when you push the button in, contacts these 2. And I mean, it seems a bit crusty, to be honest, so yeah, I'm not quite sure if I'm a big fan of these, but I'll keep them anyway. And whilst we're doing front panel items, we also have these lovely little meters here. This one is for volts, 0 to 50 volts, and this one is amps. And one interesting point about those two meters is that down here and down here they have numbers, they have numbers that could be interpreted as years. So this one says 1965 and this one says 1958. If you assume that the first date is when the thing was made, you would assume that maybe this meter, the 1965 one, was replaced at some point. But yeah, we'll look at that later, so let's put these aside as well. Then we have one adjustable resistor. You've got your fixed resistance between those two terminals, and this is the Viper, which you can place at any point and clamp shut. Now here we have the label. I'm not quite sure if you can make it out. It says 1.27 ohms, and it was made by the British Electric Resistance Co. Limited, also known as Berco apparently. So yeah, very specific company name. And on the topic of resistors, we also have our shunt resistor, which goes with that ammeter down there. And I'm not quite sure if you are able to read that. It's supposed to produce 75 millivolts, that matches the meter, at 250 amps, which, if you do the math, means that the shunt resistor has a resistance of 300 microohms. So I think that's officially the lowest value resistor I own. So yeah, I'll keep that with the meter because that's where it's supposed to go with. And it would appear that our friends at Berco were at it again with these large resistors here, which you may remember are in the current path of the lamp. This particular one is a 0.196 ohms resistor, and that's the one with the different tabs on it. And we obviously also have this one here, which on here actually says 0.493 ohms, and I measured around 500 milliohms, so that's actually quite good. And the last appearance of Berco is with this handful of potentiometers here. Again, if you look at those, it says Berco on here, and down here it says British made, patent applied for. So let's move on to other passive components, namely capacitors. First up we have this guy here, which appears to be a 10 microfarad 150 volt DC metallized paper capacitor of all things. Moving on, we have this guy here, which is a 0.1 microfarad 2.5 kilovolt capacitor. You've got two different voltage ratings for different temperatures. So you've got 2.5 kilovolt for 60 degrees Celsius, and you've got 2 kilovolts for 71 degrees Celsius. And it's just quite curious that they have 71 degrees, which is really oddly specific and, well, quite an odd value really. But yeah, I mean, this will be quite useful, and it's also got its bleeder resistor up here, which no doubt is a good idea to have on there. And the last capacitors are these guys here, which are from the timing circuits. Now this is where it gets really interesting. One point about those in general is that they had this plastic sleeving on them, and that had turned really sticky. It was like honey or something, and yeah, they were really extremely yucky to hold, and it took me a while to actually get my hands cleaned after that. Unfortunately, the print on those did come off with IPA, so they're still a bit sticky, unfortunately. Anyway, we've got three with 5000 microfarads, which I'll put aside over here. And most interestingly, we have one with 2500 microfarads, and this one down here says October 57. So that's really good, because this will help us date this instrument, because now we have October 57 on this capacitor, and also 58 on the ammeter here. So that would really point towards the fact that this whole thing was made in probably 58 then, and that the voltmeter was probably a later addition. Maybe the original one got fried or something. And now we're getting to the point where it gets interesting for classic car enthusiasts. This here is one of the solenoids. You can see it's got these two terminals here where the current goes through, and those two here for the solenoid. And let's just take the cover off and have a quick look at what's inside. Ta-da! This is what it looks inside. You have this very large solenoid here which pulls down on this contact here. It goes between those two copper bars, which then makes contact between those two terminals. And next up is the little solenoid, which was used on the high voltage generator. And this one clearly was a repurposed automotive part because it has things like B- and STA on here. So I would imagine that this was used for starter motors, for example. And I think it's actually the same one for this one as well, because in here this terminal is labeled, well, I can't see this, B+ as well, so I assume that both of these were actually used in cars or trucks or something, and then were just repurposed by the maker of this control panel, which is, you know, a good idea, because if someone else has gone through the trouble of making switches for tens and hundreds of amps, then why should you do it? And here we have the final engine part, and this one is really exciting because I didn't even know what it was or that it even existed, and had looked it up myself, and it's really exciting. So what this is, it's a booster coil for a magneto-ignition system. Obviously, if you want any more detailed information, you can look it up yourself. So what it basically is, it's a self-resonating high voltage generator that is just turned on as you start your engine. So it provides sparks as you turn on the engine, and then once the engine is running, your normal magneto takes over. And with the back cover removed, we can actually see how this thing works. Basically, the main body is just a normal ignition coil, and down here you have this little contact, and this basically works like an interrupter in a normal ignition system. So you've got the current going through the ignition coil and through that contact here, and as you power it on, this contact is closed and current flows. But as the current flows, a magnetic field builds up which pulls this contact down. The circuit opens, you get your spark from the ignition coil, but at the same time the magnetic field goes away and this contact closes again, and this whole thing repeats over and over again. So this will oscillate back and forth at quite a high frequency to generate a steady, well, stream of pulses, high voltage pulses really. And this is also the reason why the control panel sounded so angry and, well, just electromechanical when you hit the strike button, because this guy here vibrates and makes the high voltage. And when we're talking about high voltage, we obviously mustn't forget our little friend, the spark gap here, which we've seen in quite some detail already. Interestingly, it does have some white powder in it. I'm not quite sure if you can see that. I presume it's fiendishly toxic, and I'll just put this to the side and hope it doesn't break. You may remember that earlier in the video I told you that this control panel was semiconductor free, but depending on how you define semiconductor, this might actually have been a lie, because there are these guys in there as well. And these are basically diodes. They are rectifiers, and you even have a part number on here. And apparently they were used in TVs and things like that before silicon rectifiers or germanium even came about. What they are, I'm not quite sure which type they are, but they're either selenium or copper oxide or something like that. Compared to modern rectifiers, these guys aren't that great. Each junction has a forward voltage of about 1 volt and can only hold up to a reverse voltage of 10, 20, 30 volts, something in that area. Now in this control panel they were used for high voltage, so you had reverse voltages of, I don't know, 1000 volts or so maybe per unit. And the way they achieved that is they just stacked lots of little discs inside these tubes, and that's how you got your high reverse voltage. But it also means that your forward voltage is very large. And I hooked it up to the power supply, and at 120 volts forward voltage we only get 4 milliamps through. So you think about that as a diode with 120 volts forward voltage. So yeah, it's not really a very good diode at all. But I suppose people might still want to have them as spares for whatever other old instruments they have, so I'll put them aside as well. And here is another bit from the high voltage system, a adorable little ceramic standoff. I'll definitely keep this one around in case I ever get around to do some high voltage experiments. It's really quite adorable, I think. And the final piece of the high voltage system is obviously the very chunky transformer, which steps up the voltage generated by the boost coil over there to something that can actually strike the lamp. And since my friend Steve from SDG Electronics very kindly lent me his LCR meter here, I thought we might as well try and measure the inductances of the different windings on here and figure out if we can get the winding ratio from that. So first of all, let's measure the lower voltage side, which I believe is between here and there. Note that I don't have to actually get to the ends because the rubber insulation is all broken already. And we're measuring about 520 or so microhenries. And the high voltage side is between here. And we get about 8.3-ish millihenry on the high voltage side. Now, as you may know, the inductance of a coil is proportional to the square of the number of turns, and the voltage ratio is also proportional to the number of turns. So it basically means that if we know the ratio of inductances, we have to take the square root of that and we'll get the ratio of voltages. So if we take our trusty old calculator here and input our 8.2 millihenries over our, what is the other one, 520 microhenries, we get a ratio of 3.97, so let's call that 4. So that tells us that this transformer would step up the voltage by approximately a factor of 4. Now if we look at, say, this capacitor here, that has a working voltage of, I don't know, 2.5 kilovolts, something like that. So we would expect the output of this transformer to be maybe just under 10 kilovolts or so maybe. And to wrap everything up, let's just look at the final few items. We have those two relays here, which are, well, not terribly exciting to be honest. Let's just put them over there. We have this original 3-pole plug and socket. Not quite sure what that might have been used, but well, it might be useful at some point. There is also this more modern 2-pole socket and plug, which again might come in handy at some point, so I'll keep that. And lastly, there is of course the little red indicator light from the front panel, which is very nice and shiny and contains a 24-volt light bulb. So that is obviously from an era way before LEDs were even dreamed of. And that goes together again and will be placed down here with all the other items. And really, I think that's all there is to say about the parts I got from this control panel. As I said, I was in two minds about taking it apart, but as I said, it was just way too big, way too heavy, and not really useful enough to justify keeping around. However, if you want any of those parts to fix your own unit, either a similar control panel or your old car or airplane, please do let me know. I'm more than happy to give you any of the parts you might need to fix up one of your own vintage devices. Anyway, I hope you liked that dissection of a slightly unusual piece of kit, and hopefully I'll have some more electronic engineering focused videos in the future. But yeah, until then, thank you very much for watching. And when it switch, so let's see what happens when I hit that nice red strike button here. And we see we get a breakdown in the paper.